Okay, let's take a break from parallel lines and let's talk about perpendicular lines today. So if you remember, perpendicular lines are two lines that intersect to create a right angle. Say they look something like this. So we can have, for example, line A and line B. Remember, these could also be line segments. And as long as you know they are intersecting to make this right angle, then we can say that these lines are perpendicular. And the sign for perpendicular is this upside down T. So again, this means perpendicular. Okay, so a couple of things we're going to do with our perpendicular lines. We're going to have a few theorems we're going to look at later on. But first, let's talk about what we call a distance from a point to a line. And there's lots of distances you can calculate from a point to a line. But here we're going to talk about the shortest. So when I'm asking you to find the distance in this diagram, in this section, we're going to be looking at the shortest distance. And that shortest distance is going to be the perpendicular distance from the point to the line or line segment. So let's go ahead and write that down. All right, so again, we're defining the distance as the perpendicular distance from a point to a line or a line segment. So if you look at this example below, I have point B and line L. And you're probably thinking, well, if you want me to find the distance, what are you talking about? Because I can draw a line. Oops. Here we go. I could draw a line here, right? I can draw a distance here. I can draw a distance anywhere, all over the place, right? But so it's really unclear, so we need that definition. So if we look at that definition, we're looking at the perpendicular distance. So the actual distance I'm going to have you measure or calculate would be this one right here. So this is this distance we are talking about. This is going to be your shortest segment. So again, just to be really clear, unless I'm asking you for a specific segment length, so if I had like BA and A is way out here, and ask you to find that. So unless I tell you to find that specific segment, I'm asking you for the shortest distance. So we usually think human nature, we want to find the shortest distance from one point to the next. So here our shortest distance is going to be the perpendicular segment. Okay, so let's take a look at example 1 and 2 questions here. A, what is the shortest segment from A to line CB? So here all I'm asking you to do is name it. So if you take a look at the diagram, you might think, well, how do I know what's the shortest segment? So remember, when you're saying shortest segment, you should automatically be thinking perpendicular segment. So that's right now in my mind. So sorry, this should say segment. Make that a little clearer. So look at the diagram. What is perpendicular? Look for the right angle. And I'm going to see this perpendicular segment right over here, AP. So that means the answer to this question is AP, right? And that's perpendicular, or it's the shortest because it's perpendicular. So I'm just going to write that in parentheses so you can remember that, right? Shortest because it's perpendicular, right? From the point to the line, okay? So now the question is, well, what do you mean by solve for x? Take a look at B. X is right over here. We have this x plus 9, right? How does that factor into what we're doing? So remember, our shortest segment is AP. So no matter what, AP is the smallest in measure. So if you look at this x plus 9, that's CA, this segment right here, doesn't matter what it is, it's going to be bigger than than PA. So you can write an inequality. So no matter what, AP is going to be the smallest, so it's going to be less than x plus 9, okay? Or sorry, let's use notation here. So it's going to be less than CA, that measurement, and then substitute, okay? 12 is going to be less than x plus 9. Then use your algebra, subtract 9 from both sides, and we are going to see that x is greater than 3. And I don't care if you write this as 3 is less than x or x is greater than 3, they mean the same thing. It's up to you and how you want to write that order. Okay. But again, this is a little tricky. We're not writing an equation. It's going to be an inequality because that side, CA or AC, is not going to be the same length or even smaller than AP. So we want to use the inequality sign to create the problem. Okay, let's take a look at some perpendicular line theorems to help us figure out what to do when we're looking to prove something's perpendicular or if we're given some information about perpendicular lines. So let's go ahead and look at the first one. Okay, so this first theorem, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if you look at the hypothesis in this conditional statement, there's two things that we need to happen. We need to have a linear pair and they need to be congruent angles. So if you're given this, then we can conclude that the lines are perpendicular. So if you take a look at the diagram, this would be what you're given. So you should see two things happening. One, angle 1 and angle 2 are a linear pair. And you'll also notice from the notation here, angle 1 is congruent to angle 2. So if we have this information, we can conclude and jump straight to it and say L is perpendicular to M. And this is a super simple theorem to prove. All you have to do is remember a linear pair is supplementary, so they add up to 180. And since these two angles 1 and 2 are congruent, they've got to be 90. And by definition, a perpendicular, L and M would be perpendicular since perpendicular lines intersect at 90-degree angles. So that's our first theorem. All right, let's go ahead now and take a look at the second one. So theorem number 2, in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So look at the key information in this statement as well. So our transversal is perpendicular to one line, and these lines have to be parallel. So we've got to be perpendicular to one, and then the two lines that we're looking at have to be parallel. If that's true, then that transversal is perpendicular to the other line. Okay, so let's take a look at the diagram and you can see what I'm talking about here. So this is what you'd have to be given right here. We need to be given two things, that the transversal A is perpendicular to one of those parallel lines. So A is perpendicular to B here by definition because we see that right angle at that intersection. And we also need to know that B is parallel to C. So if we have that information, then we can go ahead and say, well, then A should also be perpendicular to C. And that's a super easy one to look at because you can use your corresponding angles postulate, right? If this is a right angle right here, then down here it's also a right angle, and by definition, we've got perpendicular. So super easy to prove. Okay, one more, and we'll do one example. So theorem number 3 today. This third theorem is pretty much the converse of that second one. So now we're saying, well, if I don't know two lines are parallel, but I know two coplanar lines are perpendicular to the same line, then I can say those coplanar lines are parallel to each other. And you'll see this just works because of the converse of the corresponding angles postulate. And that's a great way to prove this. So again, you're given certain pieces of information. So you need to know we've got two lines that are perpendicular to the same line. So, right, two lines perpendicular to the same line, right? So we've got to have that for sure. If we have that, then we know the lines are parallel. So basically, you should have a transversal that's perpendicular to at least two of the lines it's intersecting. If that's true, then those intersected lines are parallel. So again, the converse of what we just looked at in the second theorem. So you have to be given two things here, right? X is perpendicular to Z in the diagram, and I just drew it a little differently so you guys can see we're not always going to look at them in a horizontal or vertical position. It can be shown in any way. Just look for the key pieces. So we see that X is perpendicular to Z by definition. Again, see this right angle. That's the key thing we're looking for. Then we'll also notice that right angle for Y and Z. So that also tells us Y is perpendicular to Z. So if we have these two pieces of information, then I can say that x should be parallel to y. And that's because, again, of the converse of the corresponding angles postulate. And that's a great way to prove this theorem. So notice this time you're going to need two pieces of information to use any of these theorems. Make sure you're checking off kind of like a mental checklist. Do I have both pieces? If so, then I can make a conclusion. All right, so let's take a look at this final example. Let's write a proof. Okay, remember, don't be freaked out by the proof. Let's work backwards if we need to, or take a look at what we're given and work our way there. So look at your given, and we are shown that AD is parallel to BC. Awesome. That means using AB or DC as a transversal, I can talk about alternate interior angles, alternate exterior angles, interior angles, and all that. And then we've got some other perpendicular lines, right? AD is perpendicular to AB, which shows me I've got 8 right angles, basically. BC is perpendicular to DC. What does that tell me? I've got, I've got 4 right angles here and 4 right angles there. Awesome. How am I going to use that to prove AB is parallel to DC? Well, think about it. To prove lines parallel, we've got a bunch of options. So we can think about using any of those converses that we used in the last section. So converse of the alternate interior angles theorem, converse of the corresponding angles theorem, converse of the alternate exterior angles theorem, and we can also talk about, oops, that should be postulate here. And we can also talk about the converse of the same side interior angles theorem. All right, so that's what we learned about in the past, but now we can add one more to our list. Think about that final theorem we talked about earlier in this video, just now. This one doesn't have a super nice name we can use, but we know if we have 2 lines perpendicular to a transversal, then 2 lines are parallel. So this is the new one right here. We can say, if I can show that AB is perpendicular to AD and DC is also perpendicular to AD, then I've got parallel lines. So same thing here. If I can figure out AB is perpendicular to BC and DC is also perpendicular to BC, then I've got some parallel lines, right? So that's what we're basically looking for, okay? So you can do this in a number of ways, and I'm actually going to focus on this one right here. So how am I going to use this theorem to prove the lines are parallel? And you've got a lot of options, okay? So let's take a look at some of these angles. And for the interest of being really clear, I'm going to name them, okay? Okay, so let's go ahead and call this angle 1 and call this angle 2. All right, so I'm going to go ahead and write my proof. I'm going to actually delete all this stuff with the theorem so I have space so you guys can see the diagram as I'm going through it. But again, something you can do when you're doing your proofs is just like what I did right here, the stuff I'm erasing right now. It was like a checklist saying, well, how am I going to get to that final statement I'm trying to prove, right? And you can work backwards. I had 5 options, and then you can look at what you're given and kind of work your way to AB is parallel to DC. All right, so let's clear this all away. Cool. And let's write our proof. I'm going to go ahead and do a flowchart proof because I really want you guys to see the flow of logic. And hopefully you can see where arrows go together here. But you can also convert this to a two-column proof. Like I said before, I don't care about your format as long as it makes sense. You're cool. Okay, so what I want to do here is start off with my given. So it's really important for me to say that, well, AD is perpendicular to AB. Okay. So that's a given. Because like I said earlier, I want to use the fact that if I can have two lines perpendicular to the same line, I can get parallel lines. And again, this isn't the only way you can do it. This is one way you can do it. And I wanted to use the new theorem to show it to you. All right, I'm going to go ahead and write the other givens. So BC is perpendicular to DC. Again, that's a given. I'm putting all my givens in separate boxes because I want to show you guys where it all comes together. Okay, and I realized I need to put another given here. So I'm going to go ahead and put AD is parallel to BC right on top here. And I'll just make my flowchart kind of work down and to the side if I need to go that way. All right, so these are my givens. So remember, use what you know. I know AD is parallel to BC, and if I can show this angle too is a right angle, or any of these angles really in this corner as a right angle, I can show that AB is perpendicular to BC, which is what's going to help me get to my final statement, because that's the theorem I'm trying to use here. So if I know that AD is parallel to BC, I know that angle 1 is congruent to angle 2 because they are alternate interior angles. Okay? Since I know that AD is perpendicular to AB, by definition, that tells me angle 1 is a right angle. All right? And that's your definition of perpendicular. Okay, so if I know angle 1 is a right angle, then I can take that and say, all right, right angles are 90 degrees, so the measure of angle 1 is equal to 90 degrees by your definition of right angle. Okay. Now, remember, I want this angle 1 to translate to angle 2 because really I don't care about this line AD. I really want to focus on BC and show that BC is also perpendicular to AB. And then I could say that AB is parallel to DC, right? So from here, I know angle 1 is congruent to angle 2. That works really nicely in saying that the measures will be equal by using my definition of congruent. So again, if you think about that logic I just said, I was trying to take away the 1 because really I don't care about this, right? What I want to do now is I want to show that this angle 2 is also a right angle. So I can now substitute. All right, so let's go ahead and substitute and say that, well, 90 is equal to the measure of angle 2, right? That's my substitution. What does this mean if the measure of angle 2 is 90? Well, it means angle 2 is a right angle. And that's your definition of right angle. Sorry, this is an angle symbol. Which miraculously now shows us that AB is perpendicular to BC. Careful of your notation, okay? And this is your definition of perpendicular once more. All right, just scroll down just a little bit. All right, so now that I know AB is perpendicular to BC, and notice BC is perpendicular to DC. So see how this line BC repeats? Now we know BC is perpendicular to both of these lines, right? So right here we've got a 90-degree angle, right here we've got a 90-degree angle. So this BC is that key transversal. So since we have two 90-degree angles, what we can say now is we can put it all together and, oops, let me clear that up a little, and say, now that I've got two perpendicular lines that are perpendicular to the same transversal, AB is parallel to DC. So again, you can see it's that BC that repeated. BC right here, BC right here, cut them out. AB is parallel to DC. And again, sadly, no real name for this theorem, so I've just been writing in shorthand. 2 lines perpendicular to same line, lines parallel. So something like that to abbreviate the theorem. Okay, so that is it. You want to be able to use the theorems we just learned about on perpendicular lines. All right, again, this isn't the only way to prove it. This is kind of long with a lot of little details here, but you could have also used the definition of right angle to show that we've got, 2 right angles here, so the converse of the corresponding angles would have worked, right? You could have done these same side interior angles are supplementary, so this is 90, then we've got converse of the same side interior angles theorem. So a lot you could have used here. It all depends on what you see, okay? Make sure you come to class with questions. We'll be practicing this for the next couple of days.